Hello, I'm Bob Kowalski, and I'm here today to argue the case for using Prolog to teach just about everything. In particular, we'll talk about using Prolog to teach computing, logic, human communication, and problem solving. I will draw upon a number of sources, which you can see spread out before you here. I will build upon the work that was done in celebrating the 50 years of Prolog. I will refer to the role that Russell and Norvig argue for logic programming and Prolog in their book on artificial intelligence. I'll mention Hector Levesque's use of Prolog to teach thinking as computation to non-computing students. I'll shamelessly mention some of the points made in my own book. I'll point out some of the arguments made by Barbara Minto in her book for teaching writing and thinking to management students. I'll look at some of Sherlock Holmes' advice about how to solve problems more effectively by reasoning backwards. Thygard's argument against logic and try to turn that argument upside down against him, and bring in some examples from Alice in Wonderland and my first dragon book. So what makes Prolog special? It's not just a programming language or database language, but both, unlike other programming languages, unlike other database languages. And not only that, it's also a knowledge representation language used for significant artificial intelligence applications. Viewed as a logic, it's not really just a subset of first-order logic, as many of us have sometimes thought it to be, but it's a more natural logic, closer to natural language, with a metalogical higher order and modal order capabilities. But it's not just a computer language and not just a logic. Arguably, it's a simplified, more logical form of natural language. So why should we be teaching Prolog? It's not just because we love Prolog or because we love logic. It's because Prolog is a better way to introduce computing, a unifying approach that applies to all areas and not just to programming, for example. It's a good way to help teach human-to-human communication. That may seem a little strange, but the point of logic and its incarnation in Prolog is that language, natural language, is ambiguous. And by learning Prolog, we can learn to recognize those ambiguities and learn how to avoid them in a natural way. Moreover, viewing natural language as communication, whether it be to a computer or to a human, it helps us to appreciate more that it takes an effort to understand a communication, and that the reader or the recipient of a communication needs to process the information that's been given, and that processing is costly. And the less cost, the more efficient the communication, the easier it is for the reader. So that's one of the arguments for teaching Prolog, not only for communicating with computers, but for helping us to understand how to communicate better with other people. It's a good way to teach problem solving, to teach goal reduction, and that of course, is the nature of problem solving by computer. Prolog is imperfect and needs to be extended. And in the 50-year of Prolog book, there are plenty of ideas about how to improve and extend Prolog, but it's a good first step. And in that book, you'll find a paper of my own with a number of my colleagues where we suggest that there are ways in which Prolog can be improved, but if you're going to start somewhere, then Prolog is perhaps the best place to start. If we look at more popular views of Prolog, we'll see that it is widely regarded as a declarative programming language. And in computer science, a declarative programming language is one that focuses on the logic of computation without describing and concerning itself with control. Many languages that are declarative in this respect are focused on describing what the program should do rather than describing how it should be done. So this contrast between what is the case and what should be the case on the one hand, and how to achieve what we want to be the case, is often used to distinguish Prolog as well as other declarative programming languages from imperative languages. I want to argue that this is mistaken. I want to argue that in natural language, we both represent what is the case declaratively and also how to achieve what we want to achieve. And as my first example, I'd like to show you this alarm signal lever that can be found on the London Underground, and look at the two sentences that are displayed on the lever here. The first sentence, in effect, is an imperative sentence telling us to use the alarm signal button, or in this case, the alarm signal handle, to stop the train. To stop the train, pull the alarm signal handle. This is not what is the case. This is not describing what is the case. This is describing how to behave in emergencies. Of course, we can represent this in Prolog in a more declarative form by recognizing that the goal of stopping the train is really the conclusion that will be achieved if you perform the action of pulling the alarm signal handle. So if you pull the alarm signal handle, you stop the train. That's a declarative statement, but to stop the train, pull the alarm signal handle is an imperative, a conditional imperative. A natural language includes both. And in this case, you can see when it really matters, the natural language sentence is expressed in the conditional imperative mood. The second sentence is more classically declarative. There is a 50-pound penalty for improper use. Conclusion, there is a 50-pound penalty. Condition, you use the alarm signal handle improperly. And of course, we can turn this around. And if we use this in a goal-directed manner, we can use this rule to achieve the conclusion. So if you want to receive a 50-pound penalty, then just go ahead and use the alarm signal handle when you're not supposed to. The idea of teaching Prolog as a way of teaching thinking is not original, and Hector Levesque has presented a very good case for this in his textbook designed for non-computing students at first-year undergraduate level. And in his book, he discusses in general terms the relationship between human thinking and computing, and he looks at how human thought can be regarded as a kind of processing of ideas that can be expressed to some extent, at least, in natural language. Now, he says that a secondary goal of the book is to illustrate this notion and this relationship between thinking and computing by using the language Prolog. He calls this a secondary goal, but the vast majority of text in the book is concerned with teaching Prolog. Another major source of evidence to show that Prolog is a very good way of teaching thinking and computing is the very popular book on artificial intelligence by Russell and Norvig. And they argue that the semantics of Prolog is not really classical first-order logic, but it's closer to natural language in ways that make it appropriate for knowledge representation. And they look at an example which has come up earlier in the book, in which they want to represent in logical form the belief that King Richard has two brothers, John and Geoffrey. And the obvious way to do that is by writing two sentences. John is brother of Richard, and Geoffrey is a brother of Richard. But then they go on to say that this isn't good enough. This sentence, this conjunction, is true even if Richard has only one brother, because John and Geoffrey could be different names for the same individual. So if you want to say that Richard has two brothers, John and Geoffrey, you have to at least say and add that John is different from Geoffrey. Moreover, Richard could have other brothers besides John and Geoffrey, and so you also have to add that for every X, which is the brother of Richard, then the X is either John or Geoffrey. And of course, this is very cumbersome. And it makes first-order logic more remote from natural language. On the other hand, the authors of the book, suggest that there are other semantics that can be associated with the syntax of first-order logic, which is a kind of database semantics, indeed a Prolog-like semantics, which renders Prolog in particular closer to human natural language. Another support for my argument that we should use Prolog to teach a wide range of subjects is the book by Barbara Minto, where she presents an approach to writing for a management audience, which is based upon the idea that goals should be placed at the top of a structure to be supported by facts, potentially many facts or many beliefs at the basis of a pyramid. So this pyramid of Barbara Minto, which she argues is a good way to structure human writing and also structure human thinking, is a fundamental approach that can render both communication and thinking more effective. So in the website that describes her book, she regards and presents the pyramid principle as a technique for thinking about any subject, not just computing, as it turns out, and indeed she doesn't refer to computing at all, but instead talks about communicating your ideas about any subject. She promotes the idea of structuring thoughts and presenting them in a pyramid form, which makes it easier for your audience to understand. But not only does it help the audience, it also helps you as a writer or as a communicator to organize your own thoughts and develop your own thinking. And if you want to know more, the cost of the book is $150. On the other hand, you can just continue to watch this video for free. But the use of Prolog in education is not restricted to first-year undergraduate students or to management science students. It can be presented to quite young children using what would normally be regarded as quite sophisticated and complex computer concepts without students needing, or children in this case, needing to be made aware of that complexity. For example, we might introduce dragon stories and present them with logic programming Prolog-like sentences of the form, with a conclusion that a dragon smokes if another dragon is a parent of the dragon and the other dragon smokes. Or to put it differently, a dragon smokes if one of its parents smokes. And this is the kind of recursive definition, which when taught to a computer science student is often thought to be quite complex and hard to understand. Whereas if you present this sentence to a child, there's no need to explain recursion. It's quite clear, it seems to me, just as a sentence of natural language. Similarly, you might be able to explain to a child that a creature is healthy if it is not the case that the creature smokes, or put it more procedurally, if you like. If you want to be healthy, then you shouldn't smoke, assuming you're a creature, of course. And here we use negation as a condition of a rule or of a sentence which has the conclusion that you are healthy. Again, a concept, negation in this case, which is regarded as quite a complex notion that needs a lot of explanation if you were doing a course in computer science. And yet another example which shows that we can express quite complex relationships in logical form using Prolog. A dragon is happy if for all cases in which the dragon is a parent of another dragon, it is the case that the other dragon is healthy. Again, to put it differently, a dragon is happy if all its children are healthy. In other words, if all its children do not smoke, and of course, as putting it all together, provided you as a parent don't smoke, because if you have any children, your children will smoke and they won't be healthy and you won't be happy. And of course, I've been showing you English over here, but that English is just sugar syntax for good old-fashioned Prolog, which is perhaps a little intimidating in its symbolic form, but which could be introduced to children in a more natural language representation. To continue with an example of recursion, which I would suggest is very easy for a child to understand without needing to be educated in computer science. Suppose we assume, for example, that Alice likes logic. Suppose we assume that Alice likes the thing if the thing likes logic. This second sentence is, of course, a recursion. It defines the concept, or partially defines the concept of liking something, or in this case of Alice liking something, in terms of that something liking logic. And you might ask, is this something that would be that would require an education in computer science in order to understand? And I would suggest no, it doesn't. It has a purely declarative interpretation as well as a procedural interpretation. If you use the information expressed, for example, on line 10 to reason in a goal-directed way, then if you want, or if Alice wants to like a thing, then she should go looking for things that like logic, and she'll discover that she herself likes logic and conclude that Alice likes herself. Of course, this can all be presented in Prolog, and it can be executed in Prolog. At a later level in education, we might want to teach, say at high school level, the notion of greatest common divisor. And the standard definition of greatest common divisor can be expressed, for example, by saying that a number D is the greatest common divisor of two other numbers, N and M, if D divides both. So it is a divisor, in other words, of both N and M. On the other hand, if we want it to be the greatest common divisor, it should divide all other divisors. And so for all cases in which another number divides N and the other number divides M, in other words, the other number divides both N and M, then it is the case that that other number is less than or equal to D. And notice this standard definition of greatest common divisor uses neither recursion nor does it use iteration in the standard sense of computer programming, although it does use this notion of for all. Here, for all is a logical notion, which in theory could be, if you like, implemented in parallel. It doesn't have to be an iterated in sequence. So it's not really iteration at all. It's a logical concept. And of course, to use this in practice, we would also need to have a definition of what it means for a number to divide another number. And that would simply be defined by saying that if you divide the number, then the remainder is 0. And of course, this all has a Prolog representation underneath the hood. But to go back to the pyramid principle again, this pyramid is actually neutral. This pyramid, which could be used to structure both our thoughts and our communications, could be traversed in different directions. You can build it up, for example, in a bottom-up manner, reasoning forward to derive conclusions from conditions, or you can build it backwards, from the top down, reducing goals to sub-goals. Prolog, of course, reasons backwards. Sherlock Holmes argues that backward reasoning is difficult, and it's a technique that is worth learning. And he mentions in his book, A Study in Scarlet, that in solving a problem of the sort he's considering, the grand thing is to be able to reason backwards. That is very useful, very easy, but most people do not practice it much, and they don't practice it as much as they should. In everyday affairs, it's more useful to reason forwards, and so the other comes to be neglected. For every 50 who can reason synthetically, that is to say, forwards, there is one who can reason analytically, that is to say, backwards or top down. Now, these notions may seem unfamiliar, and poor Watson, his faithful companion, says, "I confess I do not quite follow you." But you need to follow these ideas if you want to understand backward reasoning, and if you want to be a more effective problem solver. And in particular, if you look at the Euclidean algorithm is a procedure. It's a procedure which uses backward reasoning to achieve a goal by reducing it to sub-goals. It's a recursive procedure, or maybe an iterative procedure, depending upon your point of view. And it terminates when the number that you are focusing on, the number n, is the greatest common divisor of n and n. So it is going to be a procedure which terminates when the two numbers that you want to find the greatest common divisor of are the same. Otherwise, if one of the numbers is bigger than the other, if n, for example, is bigger than m, then what you should do is you should subtract the smaller number from the bigger number, getting a smaller number instead, and then find the greatest common divisor of the smaller number, namely the difference, and the smaller of n and m. And that greatest common divisor is the greatest common divisor of the two numbers you were wanting to find in the first place. And of course, if the other way around, if m is bigger than n, then you just do the same thing, subtracting the smaller number from the bigger number. So here's a program which can be represented in Prolog. I've written it in a sugared syntax, but nonetheless, it's a Prolog program. And if you want to understand it as the Euclidean algorithm, then you cannot understand it purely declaratively. You have to understand how it is executed by reasoning backwards, reasoning top down, given two numbers m and n, checking whether one number is bigger than the other, subtracting them, and then recursively finding the greatest common divisor of the difference and the smaller number, m or n. And of course, all of this could be written in the standard syntax of Prolog. So looking more closely at the relationship between Prolog, first-order logic, and the human language of thought, we might consult, for example, this book by Paul Thagard, another introductory textbook intended for non-computer science students at early university level, looking at cognitive and studying cognitive science. In his book, Paul Thagard argues that rule-based systems, namely production systems, an alternative model of symbolic computation, that rule-based systems are different from logic, and one of their virtues is that they can easily represent strategic information about what to do or how to do what you want to do. What does he mean by this? He gives an example. He says that production rules, different from logic sentences, often contain actions that represent goals, such as if you want to go home for the weekend and you have bus fare, then you can catch a bus. So here we have a goal reduction rule. Your goal is to go home and you have a sub-goal of catching a bus. And Thagard uses examples such as these to argue that although rules in a production rule system, for example, do not have the full expressive power of ordinary formal logic, they nonetheless have enhanced computational and psychological power. So they're more, he argues, they are more suited for computation, and they're more suited as a model of human thinking. But let's look more closely at this example of his. If you want to go home on the one hand, it seems, quite close to a Prolog rule written in sugared up syntax. It has a conclusion, you can catch a bus, and it has conditions. You want to go home for the weekend, and you have bus fare. But this way of looking at the conclusion and conditions doesn't really do service to the goal reduction nature of the rule. Thagard's production rule is actually a goal reduction rule. It is expressed in the forward direction, so to speak, where one of the conditions is that you want to go home for the weekend, another that you have the bus fare, and it has a conclusion that you can catch a bus. But this is basically expressing in a forward manner what would ordinarily be understood as reasoning backwards from goals to sub-goals in a pyramid structure. Such goal reduction rules can be obtained by logic programs and Prolog programs, reasoning backwards, reversing the relationship between the conclusion and the condition. So the conclusion is that you go home for the weekend if you have bus fare and you catch a bus. So Thagard's argument, in other words, against logic and in favor of production rules is equally an argument for Prolog, for goal reduction rules, and for viewing Prolog not only as a declarative language, but also as a language which allows us to explain how to achieve our goals. So natural language, as Thagard describes it, and Prolog both express declarative knowledge about what is the case, as well as imperative knowledge about how to obtain the goals that you want to achieve. Before I finish, I want to dive a little bit into some of the more exotic capabilities of Prolog, which from a computer science point of view are often described as the use of code as data, meaning that a program can be manipulated by other programs. I want to suggest that this facility is not just convenient for computer programming, but it's also essential for modeling human thinking and human communication. And given this capability of code as data, we can obtain the capabilities of higher order, modal order, meta order logics. So let's look at Alice in Wonderland and her invitation to attend a tea party. So let's suppose Alice attends the tea party. The Mad Hatter and Dormouse also attend the tea party, as you can see illustrated here. But suppose that a creature is prohibited from attending the tea party if it is not the case that the creature is approved or the attendance of the creature is approved. So here you see immediately that we have code as data in the sense that the concepts of prohibition and of approval are concepts that apply to sentences or such as attending a party. Alice attends a party, but she may be approved. Her attendance may be approved or it may not be approved. So this notion of prohibition, for example, is associated with so-called deontic logics, normally expressed in what are called modal logics, which have a complex semantics and are subject to various so-called paradoxes. But in Prolog, in Prolog, as you see here, it's very natural and very easy to simply express what we would ordinarily express in ordinary natural language without paradox. In particular, if we have prohibitions or obligations, and if those obligations or prohibitions are violated, we can describe what the consequences might be. So, for example, if a creature attends a party and is prohibited from doing so, then the creature will be punished. And depending upon whether the creature is a lowly creature or a lofty creature, the punishment might be one of different sorts. So in this imaginary example, I've suggested that lowly creatures should be banished, their punishment should be banished, but lofty creatures should get away more lightly simply with scolding. And if we assume, for example, that Alice attends the tea party and her attendance is approved, the Mad Hatter is lofty and the Dormouse is lowly, then we can start to draw some conclusions. And of course, to do that using Prolog, we would convert the sugar into Prolog-like syntactic form, and we could feed our queries into a Prolog execution engine. And if the query is, in this case, who is punished with what kind of sanction, query what creature is punished with what sort of sanction, then the answer would be that the Dormouse is punished with banishment and the Mad Hatter is punished with scolding. Now, this rather fanciful example might be suitable for introducing children to code as data, to deontic logic in a quite unintimidating and maybe easy to assimilate fashion. But it's not all just fun and games, because this kind of homoiconicity can be used for complex practical applications in legal domain in particular. So here's an example taken from a loan agreement between a borrower and a lender. and the borrower enters into an obligation to repay the lender. The borrower also enters into other obligations, such as not falling into debt. And if any of these obligations are violated, either by performing an action or not performing an action, or by entering a state of affairs, what we would call in both cases an eventuality. If the borrower has an eventuality and the borrower fails to satisfy the obligation that the eventuality should come about, and if the lender notices that this failure has taken place and notifies the borrower of this failure on some date, let's say date D1, that the borrower has failed to satisfy the obligation, for example, not to repay some part of the loan in a timely manner. And 2 days after the notification, D2, a default occurs, and that in turn has legal consequences, which are not very nice for the borrower, presumably. This default occurs if the borrower has not cured the failure before this deadline D2. So D2 is a deadline that is given to the borrower that the borrower must repay. Rather, the borrower must cure the failure. So this gives you an idea of how simple facilities can give rise to complex applications. And of course, we have our underlying Prolog symbolic form. So let me say, if you want to explore these ideas further, then please consult some of these other sources. And let me conclude by saying that Prolog is a great way to introduce computing, a good way, a great way to introduce logic in a more natural, more congenial manner. It helps to understand human communication and to make it more effective. And it can also be used to help teach problem solving. These conclusions may not be to everyone's satisfaction. They undermine conventional computer science views of what one should do to teach computing, but I think it's maybe one that should be investigated by looking further afield, not just inside computer science practice. Thank you.